You are already moving at nearly 1,700 miles an hour, carried by the Earth's spin, and your body has never once complained. Light speed is 600,000 times faster than that, and your body would not survive the difference quietly. In 2015, a Russian cosmonaut named Gennady Padalka came home from orbit measurably younger than the people who welcomed him home. And most people still think light speed is a problem for physics, not for bodies. At 50% of light speed, a millimeter of interstellar dust hits a hull with the force of a hand grenade. At 99%, the empty space in front of you turns into a wall of radiation that no shielding ever built on Earth has stopped. At 99.99%, your own mass becomes too heavy for any engine to push you one further mile. Tonight, we'll find the exact speed where your skin stops being safe. We'll watch the stars ahead of you collapse into a single blinding point. We'll follow your own heartbeat as it falls out of step with everyone you love. And we'll reach the one wall in this universe no human body has ever crossed, and almost certainly never will. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. Let's begin. At half the speed of light, the empty space directly ahead of a ship stops behaving like emptiness. Every stray hydrogen atom drifting between the stars. Atoms so sparse that a cubic meter of true interstellar space holds, on average, less than one of them, slams into a hull with the energy of a subatomic particle fired from an accelerator built to smash matter apart, because velocity is the only ingredient physics needs to turn nothing into something lethal. A ship does not have to reach light speed to become dangerous to ride inside. It only has to get partway there. This is the part of the journey almost no account of interstellar travel spends any real time on. Not the destination, not the exotic mathematics of approaching C, but the years of gradual acceleration in between, during which a human body sits inside a hull that is being slowly, invisibly sandblasted by the very universe it is trying to cross. Here is what the sparseness of space was always hiding. Interstellar hydrogen is not a hazard because there is much of it. It is a hazard because of what speed does to the little there is. A single proton, sitting still, is among the most harmless things in existence. You pass through trillions of them every second without noticing. Accelerate the frame around that same proton to a large fraction of light speed. And from the ship's perspective, that proton is no longer drifting. It is incoming. Its effective energy climbs by the same runaway factor that governs everything else at these velocities, until what was once inert becomes, functionally, cosmic ray bombardment. The kind of radiation normally reserved for the upper atmosphere or the depths of particle physics labs, now arriving continuously, from directly ahead, for the entire length of the voyage. Would your eyes still show you stars out there, or just a single point of blinding light where all of them used to be? Is there a speed at which empty space itself becomes something you cannot safely touch? Does your heart even register any of this? Or does it go on keeping its own schedule regardless of how fast the ship outside it is moving? And is there a wall your own body reaches long before the physics of light speed ever does? Those four questions are the shape of everything still ahead tonight. And the answer to the first one is already less comforting than you'd like. Shielding helps, but shielding is a trade, not a solution. Layers of mass water, polyethylene, the ship's own hull absorbs some of the incoming bombardment by converting it into heat and secondary particles, which then have to be dealt with in turn. Every centimeter of protection is also a centimeter of mass that then has to be accelerated, which means the ship's designers are permanently negotiating between a traveler's survival and the sheer, compounding cost of hauling their protection along for the ride. There is no thickness of shielding that solves the problem outright. There is only a thickness that buys time. Weeks, months, a full mission. Before the dose finally catches up with the body it was built to protect. And the true danger was never the hydrogen. Hydrogen is the smallest thing floating between stars. It is not the smallest thing that hits hardest. Scattered between every star system, in concentrations too thin to see and too persistent to avoid, drifts a fine haze of interstellar dust, grains of rock and ice and frozen carbon left over from the deaths of older stars, most of them smaller than a period on a printed page. At rest, a single grain like this could land on your palm, and you would need a microscope to notice it arrived. There is nothing in its resting mass that should frighten anyone. Not slightly wrong. Fundamentally wrong, because mass was never the variable that mattered. At even a modest fraction of light speed, that same grain of dust carries kinetic energy that scales not with its size, but with the square of its velocity. And velocity this extreme turns a fleck of debris into a payload. Engineers who have actually run the numbers on relativistic spacecraft. Not for this episode, but for real proposed interstellar missions. Arrive at a genuinely uncomfortable figure. A millimeter-scale grain, struck at a meaningful fraction of C, releases energy on the order of a hand grenade, detonating against the hull. Not a metaphor for danger. An actual, calculable yield delivered by something you could lose in the folds of a blanket. Hold that number. A ship crossing even a few light years of empty space at a fraction of light speed sufficient to make the journey worthwhile within a human lifetime does not encounter one such grain. It encounters a slow, continuous rain of them. Smaller impacts constantly sandblasting the leading surfaces, and larger ones arriving rarely enough to feel like chance, which is precisely what makes them impossible to fully engineer against. You cannot armor a ship against an event you can calculate the odds of, but never the timing. This is where the honest version of the story stops being about brilliant engineering and starts being about probability. Shielding can absorb the constant fine hail. No shielding thickness that remains light enough to accelerate can promise it will survive the rare, larger impact, the fist-sized fragment of an ancient comet encountered by pure chance, that no sensor gives you enough warning to dodge, because at these speeds, the distance between detection and impact collapses to fractions of a second. Every relativistic voyage humanity has ever seriously designed on paper carries this same footnote, buried without comment in the appendix. Probability of catastrophic micrometeorite impact. Non-zero, increasing with distance traveled. Impossible to reduce to zero at any acceleration worth attempting. None of this reaches the body directly. The hull absorbs the impact. The traveler, strapped in somewhere behind meters of shielding, would feel nothing more than a distant shudder, if that. But a body that survives every grain of dust the entire crossing still has to survive the crossing itself. And the thing that actually determines whether it does has nothing to do with what is happening outside the hull at all. But dust and stray atoms were never the part of this journey that would surprise a physicist. They are simply the part nobody explains to anyone else. What actually reshapes a body climbing toward these velocities begins somewhere much closer to home. Inside the ship itself, in the chair the traveler is strapped into, long before any hydrogen atom or dust grain ever gets the chance to matter. The obvious assumption is that reaching light speed is an engineering problem. Bigger engines, more fuel, a longer runway of empty space to accelerate through. Scientists confirmed decades ago that this assumption survives almost no contact with the body actually making the trip. Here is the arithmetic that makes light speed sound almost reasonable. Accelerate steadily at 1g, the same pull holding you to whatever surface you're resting on right now, and after about a year of that patient, unbroken push, a ship reaches velocities close enough to light speed that the distinction barely matters anymore, measured from the deck where its passengers stand. 1g is not exotic. It is the ordinary weight of a body standing on solid ground, sustained for 12 months instead of a moment. On paper, it is almost a gentle way to get there. The complication scientists ran into the moment they tried to make that year survivable is not about fuel efficiency at all. It is about the fact that a human body was never built to sit inside sustained thrust for that long without consequence. Fighter pilots tolerate 5 or 6G for seconds at a time, and even that leaves them briefly blacked out if their training and equipment fail them. Nobody has ever kept a human body under sustained acceleration, day after day, month after month, without relief. Because the cardiovascular system that silently manages your blood pressure while you sit here listening was designed for a planet that never asks it to work continuously against a multiplying weight. Blood pools, heart strain, bones and muscle, deprived of the ordinary rest a body expects even under 1G, begin to fail in ways gyms and treadmills were never built to counteract on a ship this size. So the real ceiling on how fast a human body can be carried toward light speed is not the size of the engine behind it. It is the body itself and the narrow, stubborn range of acceleration it can tolerate for years without breaking down before the ship ever gets close to the velocities that make the rest of this story interesting. Build an engine that pushes harder than 1G, sustained, and you have not built a faster ship. You have built a coffin that arrives at its destination carrying no one able to appreciate it, which is why every serious study of relativistic travel, however different their propulsion schemes, however exotic their fuel, converges on roughly the same number for sustained human acceleration, not because physics demands it, but because bodies do. The ship can, in principle, be built to survive far more violent departures than that. It is one of the quieter ironies of the entire proposition. Humanity may finish solving the physics of near light speed travel a long time before it finishes solving the physiology of the person meant to survive it. And even inside that gentle, survivable 1G, something else is already changing, something that has nothing to do with fuel or dust or radiation, and everything to do with the fact that the traveler's own clock has quietly stopped agreeing with the one back home. Here is the part almost nobody explains correctly, and it is the strangest fact in this entire journey. The traveler feels none of it. Not the slowing, not the stretching. There isn't even a faint hint that anything about the passage of time has changed at all. A heart beating at rest inside that ship, at half the speed of light, at 90%, at 99%, continues beating at exactly, precisely, the same rate it always has, from the only vantage point that ever mattered to the body doing the beating. Breathing feels the same. Thinking feels the same. A full night's sleep still feels like a full night's sleep. Your body will not slow down. It will simply stop keeping the same time as everyone you left behind. The mismatch only exists from outside. Someone standing on the ground, watching that ship recede, would calculate correctly, rigorously, with instruments capable of proving it, that the traveler's clock is running slow compared to their own. But the traveler, inside the ship, watching their own hands, their own pulse, their own breath, would see nothing unusual whatsoever. Time is not something you can feel yourself losing. It only reveals its debt when two clocks that were once together are finally brought back to compare notes. Pause on that. A body experiencing nothing at all out of the ordinary, and a universe outside silently deciding that years have passed for every day the body lived through. This is not an illusion or a rounding error in the mathematics. It has been measured directly, in muons and orbiting satellites and atomic clocks flown on commercial jets every single time, without exception. The traveler is not being fooled. The traveler is simply correct about their own experience, in the same way that everyone left behind is correct about theirs. Two truths, both fully real, both impossible to reconcile into a single shared now, which means the true cost of this journey was never going to arrive as pain or pressure or any sensation the body could report. It arrives later, as absence, the specific, irreversible absence of every ordinary day that would have passed at home while the traveller's own days continued, uninterrupted, feeling entirely normal. A parent waves goodbye at the age of 40 and might be waiting, still alive, decades older. When a ship returns carrying a traveller who has aged only months, or might not be waiting at all, the traveller will not have felt any of the years vanish. they will simply arrive to find that vanishing had already happened, unnoticed, the entire time, to someone else. Scientists have a name for the reversal this creates, and a spacecraft not yet built to test it. But they were wrong about one thing survivors of this journey would need most. Not fuel, not shielding. It was never even a matter of building a body strong enough to withstand the climb. What every serious account of relativistic travel underestimates is what a traveler is supposed to do with a face that has aged 40 years arriving to meet one that has aged 4. And that was only the first of the debts this speed would ask a body to pay. Every rocket equation taught in an introductory physics class assumes a comfortable fiction that doubling your fuel roughly doubles how fast you can go, the way doubling the gas in a car roughly doubles how far it can drive. That fiction survives up to a few % of light speed. Past that, it collapses. Not because engineers made an error, but because mass itself stops behaving the way a lifetime of ordinary experience insists it should. Not because the fuel runs short, because the ship itself gets heavier the faster it goes. And no quantity of additional fuel can outrun the weight. Its own combustion adds to the vehicle carrying it. This is the part almost no popular explanation states plainly enough. From the outside, an object's effective mass, the resistance it presents to being pushed any faster, climbs as its speed climbs, slowly at first, then savagely. At half the speed of light, that resistance has already grown by roughly 15% above its resting value. It sounds almost survivable. It is the leading edge of a curve that does not stay gentle for long. The consequence of that growing resistance is a number most people have never had reason to sit with. The energy required to accelerate a single kilogram to half of light speed is already in the same range as the total yield of a strategic nuclear arsenal. 1 kilogram, roughly the mass of a hardcover book, scaled up to the mass of an actual crewed vessel. Hundreds of tons of hull, shielding, water, air, and the fragile bodies those things exist to protect. The energy budget stops being a rocket fuel problem and becomes something closer to a planetary one. Every serious proposal for relativistic travel humanity has put on paper, from fusion torch designs to antimatter engines that exist only in equations, runs into this same wall long before addressing anything about radiation or dust or the traveler's own aging heart. Consider the largest machine humanity has ever built for the sole purpose of making something go fast. The Large Hadron Collider, drawing on the power of a small city, spends its entire operating budget pushing protons, particles with almost no mass at all, to 99.999991% of light speed, and not one fraction of a percent further. That is the most extreme velocity our species has ever produced, on the smallest, lightest objects available to push. A human body, and the ship built to carry it, is not a proton. It is trillions upon trillions of times heavier, asking the same impossible curve to bend for something the size of a bus, instead of something the size of nothing at all. So the popular picture of a starship is backwards. It is not a vehicle that simply burns harder to go faster. It is a machine perpetually fighting its own increasing weight, spending an ever larger fraction of its total energy just to overcome what its own velocity has added to itself. A tax that compounds the moment the engines ignite and never once offers a rebate. Half the speed of light, then, is not the halfway point of anything. It is barely the beginning of the curve that makes the rest of this story possible. And the body riding inside that curve is about to discover that mass was never the only thing changing shape. Here, finally, is the first honest answer to the question this whole night is built around. At a large fraction of light speed, a human body looking forward through a viewport would not see a starfield anymore. It would see a single, tightening ring of light, bleeding toward the center of the forward view, while everything behind fades toward black. The scattered, familiar sky people have looked up at for as long as there have been eyes to look. Orion, the Pleiades, the wide arm of the galaxy, folds itself into a shrinking bullseye directly ahead, and stays that way for as long as the ship keeps accelerating. The mechanism is called aberration, and it has nothing to do with the light traveling any differently. It is the observer that has changed, moved fast enough through space, and the angles at which light arrives get dragged forward, geometrically, the same way rain appears to slant toward you when you run through it, even on a windless day. At ordinary speeds, this effect is too small to notice. At relativistic speeds, it stops being subtle and starts rearranging the entire visible universe into a shape no eye has ever evolved to interpret. A tunnel, narrowing with every fraction of a percent closer to C until the whole of everything ahead has compressed into a single blinding point. And that point is not simply bright, it is a different color than the sky anyone has ever actually looked at. Because the same motion that bends the light's direction also compresses its wavelength. The forward sky shifts toward blue, then ultraviolet, then further still, while the sky behind reddens and dims into a darkness deeper than any night sky on Earth has ever produced. This is not artistic license. It is the direct, measured consequence of relativistic Doppler shift, confirmed in particle accelerators and verified in the light of stars falling toward black holes, now scaled up to something a human retina would have to somehow survive looking at. Think of the narrowing of your own vision the last time you stood up too fast and the edges of the room briefly darkened before your sight returned. A small, familiar collapse of the visual field that resolves in a second or two, harmless, forgotten by the time you've reached for something to steady yourself. This is that same tunnel, except it never lets go. And what waits at the center is not darkness returning to normal, but a single point of light too intense for any part of your eye, evolved for a much dimmer sky. Here's the part that changes everything about how comforting this all sounds. That shifted, tightening point of light ahead is not just beautiful, it is a preview of a problem with no elegant solution. The same mechanism, concentrating the visible sky into a single point, is, at high enough velocities, doing the identical thing to radiation the body cannot see at all, including a very old, very faint bath of light that fills every direction of the universe equally, and which a fast enough traveler would find waiting directly ahead, no longer faint, no longer harmless, and no longer behind them. Not slightly brighter, fundamentally different, because what looks, from a viewport, like the single most beautiful sight any human being has ever witnessed, is becoming, without any warning at all, the thing that ends the mission before the crew even understands why. Here is the first true answer to what actually happens to a body approaching light speed. And it arrives earlier than anyone designing these missions on paper would like. Researchers who have actually modeled relativistic interstellar flight, not as thought experiment, but as an engineering problem with real shielding masses and real radiobiology, find that a crew cruising through the interstellar medium at even a modest fraction of light speed accumulates a radiation dose that, over the length of a real mission, climbs toward levels associated with acute radiation sickness. Not at 99% of light speed, not at the exotic, headline-grabbing velocities this story keeps promising, at speeds low enough that the ship isn't even close to the interesting relativistic mathematics yet. Hold that number. A dose most people associate with a nuclear accident, delivered gradually, over years, by nothing more exotic than the ordinary thinness of interstellar space, moved through fast enough to matter. This is the detail that almost never survives contact with popular retellings of relativistic travel, because it's so much less cinematic than time dilation or an approach to infinite mass. It is simply a slow, compounding medical problem, the kind an oncologist would recognize immediately and a science fiction writer almost never mentions. A crew orbiting 250 miles above your head, aboard the International Space Station, already absorbs several times the radiation dose of someone standing on the ground, and mission planners treat that number as a genuine limit on how long any one astronaut can safely stay up there. A relativistic cruise does not multiply that already elevated dose by a modest factor. It multiplies it by however many times faster the ship is moving through the thin bath of particles that space, at rest, would have left almost entirely alone. Scientists who model these voyages routinely find shielding requirements that would make an unshielded crew compartment equivalent in absorbed dose to standing inside an operating nuclear reactor for the length of the crossing. But here's what those dose numbers don't tell you on their own. Dose is a problem you can, in principle, engineer around. More shielding, more mass, more water tanks wrapped around the crew quarters, and the numbers improve. Expensively, but they improve. Every gram of that solution is a gram the engines have to fight. But it is, at least, a solvable trade, which means the radiation dose was never going to be the wall that finally stops a human body from reaching light speed. It is a cost. Costs can be paid. What waits further along this journey is not a cost. It is a limit. A place where no quantity of shielding or clever engineering changes the answer, and no amount of money or willpower changes it either, because the thing standing in the way stops being about the ship's design and starts being about what mass itself is allowed to do. That threshold is still a long way from where this story has traveled so far, but it is where all of this is heading, and no traveler on this journey ever gets to skip it. Now add the one variable no amount of shielding mass was ever designed to solve. The body's own repair systems have a lifetime budget, and that budget was never written with a multi-year relativistic crossing in mind. Bone marrow, the tissue responsible for manufacturing the blood cells that carry oxygen and fight infection, is among the most radiation-sensitive tissue in the entire human body. More sensitive, in fact, than skin, than muscle, than almost anything else shielding is typically designed around. Chronic, low-level exposure, sustained over years, does not announce itself the way a single catastrophic dose would. It accumulates without symptoms, suppressing the production of new blood cells a little more each month until a traveler who felt entirely healthy for most of the voyage arrives at the destination with an immune system that no longer resembles the one that left. This is a fundamentally different failure mode than the acute radiation sickness the previous calculation gestured toward, and doctors treat the two very differently. Acute exposure is a single catastrophic event with a clear timeline. Chronic exposure at lower levels, spread across years, behaves more like a slow erosion. Elevated cancer risk decades later, a weakened capacity to fight ordinary infections, cataracts forming in eyes that were never struck by anything a person could point to and call the cause. Spaceflight doctors already track this distinction carefully for astronauts spending a single year in orbit. Nobody has ever had to track it for a body spending a decade inside a hull crossing true interstellar distances, because nobody has ever had a body available to study. NASA sets a career radiation limit for its astronauts calculated to keep their added lifetime cancer risk below roughly 3%, a number reached, for most astronauts, only after cumulative years spread across an entire career of missions. A single relativistic crossing, at the exposure rates the models describe, could spend that entire career allowance before the ship has covered even a modest fraction of its total journey. The traveler would not be approaching a career limit. They would be lapping it, year after year, with no agency on Earth ever having certified a human body to keep going past that point. Which means the ship, for all its engineering challenges, was never actually the fragile part of this journey. Hulls can be overbuilt. Redundant systems can be triple-checked before launch. A human body, on the other hand, arrives with exactly the immune system, exactly the bone marrow, and exactly the DNA repair mechanisms it was born with, none of which were selected by evolution with any awareness that a descendant might someday ask them to function correctly for a decade inside a radiation environment. No organism on Earth has ever needed to survive, and this is where the story of the body's slow decline briefly pauses, not because the danger has passed, but because something even stranger is happening to the traveler's own sense of direction, of forward, of which way is actually which. The longer this acceleration continues, the organ that tells you which way is down sits in a small chamber inside your inner ear, a few tiny canals of fluid and hair cells that have done their quiet work uninterrupted since long before you were born. It works by comparing the pull of gravity against the position of your head, and it cross-checks that sense constantly against whatever your eyes report about the horizon, the floor, the ceiling. On Earth, those two systems agree with each other so reliably that most people never once think about the organ responsible for the agreement. Sealed inside a ship under constant thrust, that inner ear has no reason to suspect anything is unusual. Sustained acceleration feels, physiologically, identical to gravity. It is the same force, indistinguishable by any sense organ the body owns, which is precisely why 1 g of thrust can substitute for a planet's worth of gravity for the whole of the journey. The problem is not the inner ear. The problem is what the eyes are reporting back to a brain that expects those two channels to describe the same stable world. A visual field with no scattered stars, no horizon, no familiar wash of light in every direction, replaced instead by a single tightening point of blue-white brilliance dead ahead and a deepening well of black behind, offers the brain almost none of the ordinary cues it uses to build a stable sense of orientation. Pilots call the resulting mismatch spatial disorientation, and it has ended real flights in real aircraft when a pilot's inner ear insisted one thing was true while the instruments, or the eyes, insisted on another. Sustained for minutes, spatial disorientation is dangerous. Sustained for years, inside a ship where the entire visible sky has collapsed into a shape no pilot's training ever prepared them for, nobody has ever been able to test what the human nervous system eventually does to cope. The likely answer, based on everything known about the brain's capacity to adapt, is also the unsettling one. It would adapt. Given enough time, the brain builds a new baseline out of almost any consistent input, however strange, and a traveler staring for years at a single point of light might simply come to experience that point the way anyone else experiences an ordinary sky. Unremarkable. Background. Barely noticed. Submariners report something similar after long enough beneath the surface, and polar researchers after long enough beneath a sky that never sets or never rises. The mind does not keep flagging a condition as extraordinary once it has become the only condition available to compare anything against. The universe does not stop being strange. The traveler simply runs out of the capacity to keep noticing that it is. Which raises a smaller, quieter question underneath the larger one this whole night keeps circling. If the body adapts to nearly anything given enough time, the point of light, the radiation, the weightlessness of certain systems failing slowly in the background, then what, precisely, does not adapt? What keeps insisting, the entire journey, that something has gone wrong? Here is the one part of this journey the body cannot adapt its way out of, because the body is not the part where it happens. At 90% of light speed, a traveller's clock runs at roughly 44% the rate of a clock left on the ground, which sounds, describe that plainly, almost survivable, almost like a curiosity to mention over dinner once the mission is over. What that number actually means, lived rather than calculated, is that for every year the traveller experiences aboard the ship, more than 2 years pass for everyone who did not come along. Now layer the actual shape of a human life on top of that ratio. A parent who was 50 when the ship departed is past 70 by the time the traveller, having aged perhaps 8 or 9 years by their own count, would be in any position to return. A sibling's children, unborn at launch, are raising children of their own. Entire neighbourhoods have been rebuilt. Entire technologies replaced twice over. Entire arguments settled or abandoned or simply forgotten. None of it witnessed, none of it experienced, all of it simply having happened while the traveller was doing something as ordinary as sleeping, eating, and getting slowly, gently older by a schedule that never once felt unusual from the inside. This is the part every calculation of time dilation states plainly and almost nothing prepares a person for emotionally. The people left behind are not paused, waiting politely for the traveller's return, the way a game might be paused between moves. They are living entire additional lives in the gap, falling in love, losing parents of their own, aging out of jobs and into new ones, forgetting the exact sound of a voice that, from the traveller's side, was heard only months ago. The asymmetry is not a delay. It is a debt that keeps compounding on one side of the relationship and standing motionless on the other, and there was never a version of this journey where both sides could pay it evenly. Your body did not slow down. It simply stopped keeping the same time as the people who were still aging without you. And this is not a hypothetical complaint reserved for interstellar travelers. It is already true, in miniature, for the astronaut orbiting overhead tonight, whose body has fallen some fraction of a second permanently behind everyone who stayed home. Small enough to be a scientific footnote at that scale, and identical in kind to a divergence that becomes, at 90% of light speed and beyond, the single most permanent thing a body ever does to the people who love it. Every mission profile ever sketched for truly relativistic travel has to reckon with this. In a section of the proposal, nobody enjoys writing. Crew selection stops being only a question of who can tolerate the radiation, the acceleration, the years of enclosed, recycled air. It becomes a question of who can knowingly accept an asymmetry no counselor, no training program, and no amount of preparation has ever helped a human being fully absorb in advance. Because the body doing the traveling will feel, the entire time, exactly like the ordinary body it has always been. Almost everyone who hears that, a fast enough object's mass increases, pictures the same wrong image. A traveller slowly crushed into their seat as their own body grows heavier, the way a car feels heavier climbing a hill in the wrong gear. It is a natural guess, and it is not what happens. A body inside that ship, at any speed at all, feels no additional weight from its own velocity. Not at 50% of light speed, not at 90. Not one instant before the theoretical edge of the whole affair. The increase in effective mass is real, precisely measured, and confirmed daily in particle accelerators. It is also, crucially, a property that only exists relative to somebody else. From the ship's own frame, the only frame the traveller's body actually inhabits, nothing about mass has changed at all. A cup of coffee weighs what a cup of coffee has always weighed. A dropped pen falls exactly the way it fell in a physics classroom on Earth. The traveller could run laps around the cabin, lift the same objects with the same effort, sleep just as easily as ever, entirely unaware that, to someone watching from outside, their ship's resistance to further acceleration has climbed toward numbers with no reasonable ceiling. This is one of the more disorienting lessons buried inside special relativity, and it is the reason so many popular explanations get it wrong. Mass, at these speeds, is not a single number the universe agrees on. It is a relationship between an object and whoever is doing the measuring. The engineers back home, calculating how much additional energy the engines will need to keep pushing, are dealing with a very real, very punishing number. The traveller, inside the frame where all of their own physics still applies exactly as it always has, is dealing with nothing unusual whatsoever. A second, closely related effect works the exact same way, and it is the detail that silently makes the entire journey possible for a body with only one lifetime to spend. From Earth, an observer would calculate that the ship itself has physically shortened along its direction of travel, a real, measurable contraction, not an optical illusion. The traveller notices nothing wrong with their own ship's dimensions. What the traveller notices instead is that the distance to the destination has contracted. The star system ahead rushing closer through space that has, from inside their own frame, simply gotten shorter. A crossing that would take a stationary observer many decades to wait out compresses, for the body actually making the trip into a journey a human life can plausibly contain. Neither observer is wrong. They are simply measuring two different geometries of the same single event. So the danger was never going to arrive as a crushing weight, a slow flattening, anything the body could physically register as heaviness. What actually threatens a body at these speeds has always come from outside the ship or from the ship's own machinery, never from the traveler's mass turning against them from within. And there is a second piece of this same misunderstanding that turns out to be just as important, because everything described so far has only ever been about getting up to speed. Nobody has yet asked what it costs a body to stop. Every fact so far in this journey has assumed a ship only has to do one difficult thing: get fast. But a spacecraft carrying a living crew somewhere is not a bullet. Fired once and forgotten, it has to arrive gently enough for anyone aboard to still be alive to see the destination, which means every gram of energy spent climbing toward light speed has to be spent again in reverse, tearing that same velocity back down to something a human body can survive stepping out into. This doubles the energy budget outright, and it does something less obvious to the timeline. A realistic mission profile, the kind actually sketched in relativistic spaceflight papers, accelerates at a steady 1g for the first half of the proper distance, then flips the ship around and decelerates at the same steady 1g for the second half, arriving at the destination not screaming past it but eased gently to a stop. For a journey of several dozen light years, measured from the ship's own clock, that profile costs a traveler only a handful of years of their own life. A genuinely survivable span, measured from the clock of everyone who stayed home. The very same journey costs decades, sometimes centuries, because the ship spends most of its trip at the velocities where the widest gap between the two clocks opens up. Notice what this profile rules out. There is no cruising phase where the ship simply coasts at some fixed, breathtaking fraction of light speed, engines off. The way spacecraft in most popular depictions eventually settle into a steady velocity for the long middle stretch of a voyage. A body accelerating at 1g never stops accelerating until the moment it flips to decelerate. The most extreme velocity of the entire trip is not a plateau the crew gets to inhabit and adjust to. It is a single, fleeting instant at the exact midpoint of the crossing, reached once, held for no measurable duration, and left behind again immediately as the ship begins the long, symmetrical process of slowing back down. A round trip to a star system 24 light-years away, flown this way, could plausibly cost a crew less than a decade of their own lives, while the calendar back on Earth turns over roughly 50 years. A number close enough to a working human career that mission planners have actually used it as a sobering benchmark. Whoever waves goodbye to that crew is very unlikely to be the one who welcomes them home. Push the same profile out to a target 100 light-years distant, and the ratio only sharpens. The crew might report barely 20 years of lived, felt time for the full round trip. Long, but survivable, bracketed by a launch and a landing the same body could plausibly experience firsthand. Earth, over that same interval, would complete more than a full century of its own history without them. Institutions rising and dissolving, entire scientific fields opening that did not exist at launch, and almost certainly nobody left alive at the point of departure, still present to hear how the mission actually went. At 99% of light speed, a message sent home stops behaving like a phone call and starts behaving like a letter dropped into a river. Every signal a ship transmits back toward Earth is stretched by the same relativistic Doppler effect, reshaping the visible sky. Its wavelength dragged longer, its energy diluted across a widening cone of space, until a transmission that left the ship as a clear, structured pulse arrives home as something barely distinguishable from background noise. Distance alone would already introduce a delay of years. Velocity adds a second, compounding tax on top of the delay. Not just late, but faint, degraded, harder to recover with every added light year. A crew traveling this fast is not simply out of touch. They are, for practical purposes, gone. Any request sent from Earth, a question, a piece of news, an update about a family member's health, arrives having been asked by someone who, from the ship's own accelerating vantage point, may no longer be the same age, the same person, or in some scenarios, still alive to receive the answer. Mission control on the ground has to make peace with sending messages into a delay so long that a response, if one ever meaningfully arrives, may be answering a version of the question nobody still cares about by the time it comes back. This is the quieter cousin of everything measured so far about clocks and aging. Not the divergence of two bodies growing apart in age, but the divergence of two conversations growing apart in relevance. A traveler who wanted, more than anything, to stay connected to the life left behind, discovers that connection itself obeys the same relativistic tax as everything else on this journey. There is no engineering fix for it. No more powerful transmitter changes the fundamental geometry of a signal, trying to outrun the same stretching that reshapes the ship's own view of the stars. Engineers who study deep space communication already treat this as a genuine design constraint, not a philosophical aside. Signal-to-noise calculations for a relativistic mission routinely conclude that meaningful two-way conversation effectively ends once a ship passes a certain fraction of light speed at a certain distance and does not meaningfully resume until deceleration has brought the velocity back down again near the destination. For the long, fastest middle of the crossing, a ship is not merely delayed, it is, by any practical definition of the word, unreachable. So the isolation of this journey was never going to be primarily physical. A sealed hull, a finite air supply, a crew of a handful of people, and no one else. It is temporal. A traveler moving fast enough is not merely far from home. They are, in every sense that matters to a nervous system built for immediate feedback, already living in a different chapter of time than anyone they are trying to reach. And the ship's systems, quietly and continuously, are about to demonstrate exactly how unforgiving that same stretched, unreachable universe can be to hardware as well as to hearts. 3 years into a crossing like this, a grain of interstellar dust, smaller than anything the forward sensors bother to flag, clips one of the ship's radiator fins at several hundred kilometers a second relative to the hull. The fin does not shatter. It does not need to. A pinhole, smaller than the eye of a needle, opens in the coolant line running just behind it. Coolant begins bleeding into vacuum. Pressure in the loop falls 6% over the next 11 hours. Waste heat, with nowhere efficient left to go, backs up into the hull itself. Temperature in the forward shielding tank. The same wall of water absorbing most of the incoming radiation from dead ahead. Climbs past the point where its density, and therefore its protective value, begins to drop. Nobody aboard notices any of it happening. What the crew actually experiences is a corridor 2 degrees warmer than it was the week before. The kind of drift an environmental system has corrected 100 times already, without anyone giving it a second thought. This time, the system meant to correct it is the same system now failing, degrading a little further with every hour the leak goes unpatched, because a coolant line running behind a radiator fin was never designed to be inspected mid-flight at these velocities. Meanwhile, the ship's automated systems make a decision no one aboard is awake to authorize. Remaining coolant reserves are diverted away from the 2 most heavily shielded crew berths and toward the reactor core instead. Because a reactor failure kills everyone within minutes, and a shielding failure kills only whoever is unlucky enough to be sleeping in the wrong bunk for the rest of the voyage. The logic is sound. The logic is also indifferent to who, specifically, drew that bunk assignment 3 years earlier, back on Earth, for reasons that had nothing to do with a fleck of dust nobody could have tracked in advance. Nobody chose which 2 people that would be. An algorithm did, working from a seating chart drawn up before the ship ever left the ground, before any of this was anything but a diagram in an engineering review. This is what an emergency actually looks like on a journey like this one. Not an alarm, not a scene, but a slow redistribution of risk, executed quietly, in the background, by systems doing exactly what they were built to do. There is no villain in this sequence, and no single decision anyone could have made differently with the information available at the time. That is precisely what makes it survivable as a design philosophy and unsettling as a story. The ship does not fail because something breaks catastrophically. It fails, if it ever does, through the patient accumulation of small, correct decisions that simply run out of room to keep being correct. Now multiply that single pinhole by every other component aboard, operating at the edge of its design tolerance for years on end, none of them failing all at once, all of them slowly narrowing the margin between a survivable mission and one that simply runs out of ways to compensate. Point a ship at a star system and accelerate toward it, and the target you are chasing is already lying to you before the engines finish their first burn. Every star drifts through the galaxy at its own considerable velocity, tens of kilometers a second in some arbitrary direction, and the light reaching a ship's sensors describes where that star was, however many years ago the light actually left it, not where the star is now, and certainly not where it will be when the ship, after years of travel, finally arrives close enough for the difference to matter. Lay a relativistic aberration on top of that ordinary drift, and the problem compounds. The same bending of incoming light that collapses the forward sky into a tightening point also shifts the apparent position of every individual star within that point, dragging their true angular locations toward the center of the ship's direction of travel, in a way that has nothing to do with where those stars actually are in space. A navigator watching the forward viewport is not seeing a map. They are seeing a live distortion of a map, warped by the ship's own velocity, updating continuously as that velocity climbs. This is not a defect anyone could have engineered around by trying harder. It is the geometry itself misbehaving in ways any navigator on a relativistic voyage has to correct for constantly, recalculating a true target position from a false one, using the same equations that reshape everything else in this story. Miss the correction, even slightly, and a years-long crossing can arrive at a point in space the target star vacated decades earlier. Arriving, in the most literal sense, at yesterday's address. Real mission designers already build this correction into their planning for far slower, far less extreme cases. Probes sent to outer planets are aimed not at where a moon appears to be, but at a calculated future position it has not yet reached. A relativistic crossing simply raises the stakes on a problem navigators have already solved for smaller distances for decades, without ever having to solve it while their own sense of the sky was being actively bent by their own velocity. None of this announces itself as an emergency. It behaves, instead, like an argument that never quite resolves. The instruments report one position, the models predict another, and the true answer only becomes available at the one moment nobody can afford to be wrong. The final approach, when deceleration has to begin at exactly the right instant, aimed at exactly the right point, in a sky that has spent the entire voyage refusing to hold still. And even a perfectly executed approach, aimed at exactly the right point in space, still has to answer a stranger and more basic question before that destination means anything at all. The same question that has been sitting silently underneath everything measured so far tonight, waiting for a body finally fast enough to have to answer it honestly. Every threat catalogued so far in this journey, the dust, the radiation, the isolation, the failing hardware, is a problem with a conceivable solution. More shielding, better sensors, smarter algorithms. Given enough time and money, engineers could, in principle, push each of those numbers closer to acceptable. There is exactly one number in this entire story that no amount of engineering has ever moved or ever will, and it has nothing to do with what humanity currently knows how to build. The energy required to accelerate an object with mass climbs according to a curve that does not level off, ever, no matter how much fuel is added to push it. At 50% of light speed, that curve is merely steep. At 90%, it has become brutal. At 99.99%, the energy required to add even one more decimal point of velocity exceeds what an entire star's worth of fuel, burned perfectly, could supply. The curve does not have a top. It approaches a vertical wall it never actually touches, and the wall sits exactly at the speed of light itself. Nothing crosses it. Not with more fuel, not with a cleverer engine. No technology human beings have theorized. On paper, in the centuries since Einstein first wrote the equation down, closes that gap. This is not a limitation of current rocketry the way the sound barrier was once, wrongly believed to be an absolute wall before better wings and better engines proved otherwise. The speed of light is not a wall built from insufficient cleverness. It is a boundary built into the geometry of space and time themselves, and every experiment ever run, every particle accelerator, every cosmic ray detector, every atomic clock flown on every commercial jet, has only ever confirmed it further. So the true answer to what happens to a body approaching light speed is this. The body gets closer and closer and closer still, spending exponentially more of everything. The mission has to spend for smaller and smaller gains, forever approaching a number it is mathematically forbidden to ever actually reach. 99.999999999% of light speed is not a stepping stone on the way to 100%. It is, for anything built from matter, as close as anything will ever get. A threshold with no far side, only an infinite series of increasingly expensive approaches toward a line that keeps its distance no matter how much closer the ship gets. The particle physicists at the largest accelerators on the planet already live at the edge of this same wall, spending a small nation's power grid to nudge protons, those final impossible fractions of a percent closer to something they will never actually touch. A human body, wrapped in a ship 1 billion times heavier than a proton, is not approaching a harder version of the same problem. It is approaching a wall that does not care how much heavier the thing pressed against it happens to be. Fill in the universe's oldest light, and the wall this story just described gets one final, almost absurd feature. Every direction in the sky, including the darkest, most apparently empty patch a telescope can find, is filled with a faint bath of radiation left over from an era less than 400,000 years after the universe began. The afterglow of the Big Bang itself, cooled by billions of years of cosmic expansion down to a whisper barely 3 degrees above absolute zero. It is harmless. It has always been harmless. It is, at the velocities discussed so far tonight, still harmless. It does not stay that way forever. Push a ship's velocity high enough, far beyond anything any proposed mission has seriously entertained, deep into the impossible, energy-starved final decimals of the approach to light speed, and that faint, ancient afterglow undergoes the same blue shift, already reshaping the visible stars ahead of the ship. At extreme enough values, physicists who have run the numbers arrive at a deeply strange conclusion. The coldest light in the entire universe, compressed by velocity alone, would eventually blue shift into something as fierce as the light pouring off the surface of a star, arriving from directly ahead with nowhere to hide from it. Scientists who first worked out this consequence treated it, at the time, as barely more than a mathematical curiosity, a reminder of what the equations demand at velocities so extreme that reaching them would already require more energy than exists in every star in the observable universe combined. But here's what that curiosity actually confirms. Underneath the extremity of the number, there is no version of this journey, at any speed, where getting close enough to light speed stops costing something. Even the universe's gentlest, oldest, most harmless light has a velocity at which it stops being gentle at all. There is something almost fitting about which light turns hostile last. Every other danger in this story arrives from something local, a nearby dust grain, a star's own drifting motion, a hull's own aging hardware. The afterglow of the Big Bang is the one signal in the entire sky that belongs to no star, no galaxy, no particular direction at all. It is the oldest light in existence, arriving equally from everywhere, and it is the very last thing in this universe a fast enough body would ever turn hostile. So the wall was never only about energy. It is about the fact that every input to a body's environment, dust, radiation, the sky itself, even the faint relic warmth of creation, becomes lethal at a high enough fraction of light speed, without exception, without a single loophole physicists have ever located. The exact number does not matter to a crew who will never approach anywhere near it. What matters is what the existence of that number says about the whole shape of this journey. There is no finish line here that isn't also, in some form, an ending. Return. Now, to the actual body a real mission would have to launch, rather than the idealized traveler this story has been imagining so far. That body has a bone marrow with a radiation budget, a cardiovascular system with a sustained acceleration limit, and a nervous system that has to somehow tolerate years spent inside a hull with no meaningful view of a normal sky. Every threat catalogued tonight compounds across time, which means the single most effective tool for surviving a relativistic crossing may not be a better engine or thicker shielding at all. It may be making the traveler need less of everything for longer. Researchers funded to study exactly this problem, not for light speed, but for multi-year missions to Mars, have spent years investigating medically induced torpor, a controlled, reversible slowing of human metabolism, inspired loosely by hibernation in other mammals, that could reduce a crew's oxygen consumption, food requirements, and psychological strain across long stretches of an otherwise unbearable transit. A body metabolizing at a fraction of its normal rate needs a fraction of the resources, generates a fraction of the waste heat, and by some preliminary evidence, may sustain less cumulative damage from radiation exposure per day spent in torpor than the same day spent fully awake and active. None of this touches the two walls that no medicine will ever move: the speed of light itself and the finite output of any engine pushing mass toward it. But it directly addresses almost everything this night has catalogued about the body's own fragility along the way. The marrow's radiation budget, the cardiovascular strain of sustained acceleration, the psychological toll of isolation, and a sky reduced to a single point of light. A traveler who spends most of the crossing in something closer to biological standby may arrive having aged, physically, far less than someone who stayed fully conscious the entire way. A second, independent form of time dilation, achieved not through velocity, but through simple physiology. Early trials of induced torpor in other mammals already show measurably slower cell division and altered radiation response during the deepest phases of the state, though nobody yet knows whether the effect scales safely to years rather than days, or to a human body rather than a ground squirrel. It is one of the few open questions in this entire story that medicine, not physics, gets to answer. Which means the honest answer to what happens to a body approaching light speed increasingly depends on which body is asked. A body from today, unmodified, unassisted, meets every hazard in this story at full biological cost. A body from some plausible future, aided by torpor, by radiation-resistant genetic therapies still theoretical today, by shielding materials not yet invented, might meet the same physics facing a considerably softer set of consequences. The wall at light speed itself will never move. Nearly everything standing in front of it, on the human side, still might. Here is a complication that has nothing to do with radiation, mass, or the geometry of space-time, and everything to do with the plain, awkward mathematics of technological progress. A ship launched today, cruising for decades toward a nearby star system, is not necessarily the fastest way humanity will ever manage to reach that same star system. Consider a mission departing at some achievable fraction of light speed, arriving after 40 years of Earth time have passed. If propulsion technology continues improving even modestly during those 4 decades, a second ship, launched 15 years after the first, built with better engines and thinner margins, could plausibly overtake it, arriving at the destination first, having departed second. The original crew, having endured every hazard this night has catalogued, would arrive to find the frontier already settled by people who left home considerably later than they did. Economists and mission planners who study long-horizon spaceflight call this the incentive to wait, and it is a genuine argument against launching any interstellar mission before propulsion technology has plausibly plateaued. It is also a strange new flavor of the same asymmetry haunting every traveler in this story. Not just aging differently than the people who stayed home, but potentially arriving after people who left home later than you did. Having paid every one of this journey's costs for an achievement, someone else's better funded, better timed mission might quietly erase. Some mission analyses have carried this logic to its natural, faintly absurd conclusion, that for almost any destination reachable within a human lifetime, waiting a few more decades for better engines is mathematically the faster way to get there. A body launched too early does not fail because anything went wrong aboard the ship. It fails simply by being early, in a species still capable of improving the very technology the mission depends on. That possibility does not cancel the value of going. Someone has to be first. And every later, faster ship still owes its existence to lessons only an earlier, slower one could have taught it. But it does mean the traveller accepting every hazard this night has described is also accepting, without quite saying so, the chance that being early counts for less than they hoped, in a universe that rewards patience as often as it rewards courage. History already has a version of this story in miniature. Explorers who crossed oceans on the slowest ships available to their century are remembered today for going, not for going fastest. The record of who arrived first at a given coastline mattered enormously to the people alive at the time, and mattered considerably less within a generation or two. Whatever a relativistic crew finds waiting for them, or does not find, the fact of having gone at all may end up outlasting the question of who technically got there before whom. There is no version of this problem physics can resolve, because it isn't a physics problem. It is a wager against the pace of human ingenuity, made by a body that, once the engines ignite, has no way to check the score until the ship arrives and either finds an empty star system waiting, or does not. Here is the detail buried underneath every velocity mentioned so far tonight, and it belongs less to physics than to something closer to comfort. Special relativity does not grant any single observer a privileged claim to being the one who is really moving. A traveller aboard a ship crossing the galaxy at 99% of light speed is entirely correct, by the same equations governing everything else in this story, to describe themselves as at rest, motionless, still, exactly where they have always been, while the stars, the dust, the distant destination, and everyone left behind on Earth are the ones doing the moving, rushing past at whatever velocity the traveller's own instruments measure. This is not a comforting fiction laid over a harsher truth. It is the truth, in full, as completely valid as the version where Earth stays still and the ship races away from it. Neither frame is more correct than the other. The universe simply declines to hand out a single, privileged answer to the question of who is moving and who is standing still. And every calculation in this entire episode, the dilating clocks, the contracting distances, the blue shifted sky, works out identically no matter which body gets to call itself the center. There is something almost tender hidden inside that symmetry. A traveller light years from anyone who loves them, wrapped in a hull crossing an ocean of dust and ancient radiation, gets to be, with full mathematical legitimacy, the fixed point around which the entire universe is doing the travelling. Not adrift, not lost among the stars. The still, unmoving centre of their own small and complete frame of reference, exactly as valid as the one occupied by every person waiting for them to come home. Every single body in this entire episode has been having the same experience all along without anyone pointing it out. The engineers calculating dose limits, the algorithm reassigning coolant between two bunks, the parent aging on Earth while a child crosses the galaxy. Every one of them is, in their own frame, the fixed point. Nobody in this story is the one who is truly moving. Everybody in it, simultaneously, is. Physicists have a name for the coordinates each of these bodies carries with them wherever they go. A personal, private grid of space and time that travels along with the observer, valid everywhere that observer happens to be. It is one of the stranger implications of a theory otherwise obsessed with speed limits and energy walls, that everyone in the universe, no matter how fast or slow, gets to carry their own unmoving center with them all the way to the end of the journey. There is no equation anywhere in this framework that privileges the ship over the star or the star over the ship. There never was. The privilege only ever belonged to whichever observer was doing the calculating. And tonight, it belongs to you. Not because engineers get lazier as the numbers climb, because the curve underneath every velocity in this story does not care how much progress a ship has already made. Reaching 50% of light speed and reaching 90% are not equally difficult steps along a shared scale. Each additional fraction of a percent, this deep into the approach, costs more than the entire journey required to get there in the first place. Now consider what separates 99% of light speed from 99.9%. On paper, a difference of 0.9%, small enough to sound like a rounding error. The energy required to close that gap is not 0.9% more. It is roughly 3 times the energy already spent reaching 99% in the first place. Push further. From 99.9 to 99.99, and the ratio repeats, then worsens. Every additional 9 appended to the string of decimals costs, very roughly, as much again as every 9 that came before it, combined. Here's the question that keeps physicists awake when they run these numbers seriously. At what point does chasing the next 9 stop being worth what it costs? Even a civilization with access to a meaningful fraction of a star's total energy output would eventually reach a 9 expensive enough to not be worth chasing, settling instead for whatever velocity balances mission duration against a fuel bill with no natural ceiling. There is no version of "just try harder" that changes this arithmetic. The wall does not get closer proportionally to the effort spent approaching it. It gets closer at a shrinking, ever more expensive rate for the rest of time. This is the real reason no serious mission proposal ever plans to fly at 99.999% of light speed. Despite how casually those numbers get thrown around in popular explanations of relativity, it isn't that the physics forbids it outright. This side of the true wall, it's that the cost of the attempt outpaces any conceivable benefit long before the traveler gets anywhere near testing what happens at true, unreachable light speed itself. Real mission designs, the ones taken seriously by people who have to answer for the fuel budget, cluster instead around 80 to 95% of light speed, fast enough to make the relativistic story in this episode fully real, and not 1 decimal further than the energy budget can actually justify, which means the most extreme numbers in this entire night, the tightening ring of light, the century-scale gap between a traveler and everyone they loved, the wall no mass has ever crossed, were never really about some ship, someday, actually reaching them. They describe the shape of the curve a body would be riding. However far up it any real mission ever gets, the curve does not need to be finished to be true, which is, perhaps, the only genuinely stable thing in this entire journey. Not a place or a velocity, not a destination reached or a wall never crossed, but the plain relativistic fact that no matter how fast a body moves, it never once stops being the place from which the rest of the universe is measured. Every hazard catalogued so far assumes a mission committed to speed, a crew accelerating hard, chasing a large fraction of light speed, absorbing every consequence that comes with it. There has always been a second option on the table, less cinematic, and in some ways far more humane. A generation ship, cruising at a modest, survivable fraction of light speed, perhaps 1 or 2%, nothing close to the velocities discussed tonight. Trades speed for gentleness. No relativistic mass wall. No blue-shifted sky turning hostile. Radiation dose stays comfortably within a normal career limit for the entire crossing. The interstellar medium at those speeds behaves almost the way common sense expects it to. Sparse, survivable, unremarkable. The cost of that gentleness is time, measured not in years but in generations. Centuries aboard a self-sustaining vessel, with nobody alive at launch surviving to see the arrival, and nobody arriving who ever knew the world the ship departed from. At those speeds, nearly every hazard catalogued so far in this episode simply loosens its grip. Dust impacts stay survivable. Radiation stays within a normal lifetime's exposure. The forward sky stays recognizably a sky. Stars still scattered where a human eye expects to find them, rather than folded into a single tightening point of blue-white light. This is an entirely different kind of hazard. One this story has not needed to catalogue because it isn't physical at all. It is social, generational, psychological. An entire closed society raised inside a hull, tasked with remaining functional and purposeful across a span of time, longer than most civilizations have managed to hold themselves together on an entire planet with room to roam. Historians who study the collapse of isolated societies have more to say about whether such a mission survives than any physicist calculating shielding mass. Every person born aboard such a ship would live and die between the stars, having chosen none of it, inheriting a destination as an obligation rather than a dream. No relativistic traveler in this story faces quite that particular weight. The crew, climbing toward 90% of light speed at least, chose the risk themselves, aware of exactly what it would cost their own single body. A generation ship spreads the same journey across bodies that never got a vote, asking each new arrival to carry a promise made by ancestors none of them ever met. So the true choice this entire episode has been circling, without quite naming it, is not between danger and safety. It is between two different kinds of cost, paid by two different kinds of body. The relativistic ship asks an individual traveler to absorb an enormous, concentrated risk across a single, accelerated lifetime. The generation ship asks an entire lineage to absorb a smaller, distributed risk across centuries nobody currently alive will ever personally see resolved. Neither option removes the cost. Both simply decide who and when gets asked to pay it. Every mission profile described so far, whether generation ship or relativistic sprint, depends on the same rhythm. Accelerate, then eventually decelerate, a body's velocity rising and falling rather than holding steady in one direction forever. That rhythm resolves an old puzzle about time dilation that trips up nearly everyone who first encounters it, usually phrased as a contradiction. If all motion is relative, why should the travelling twin age less than the twin who stayed home, rather than each of them simply seeing the other as the one who is really moving? The answer was never a contradiction. It was a clue that got buried under a confusing name. The two twins are not equivalent, because only one of them ever changes velocity, accelerating away from Earth, decelerating to turn around, accelerating again to come home, decelerating one final time to land. Each of those turns is a real, physical event, felt in the body as genuine force, measurable by an accelerometer, even with every window covered. It is precisely those felt turns that break the symmetry the paradox depends on. The stay-at-home twin drifts through a single, uninterrupted stretch of space-time. The travelling twin's path bends, repeatedly, in ways only their own body ever experiences directly. And it is that bending, not the relative velocity alone, that accounts for the entire age gap waiting at the reunion. Which means the very same accelerations that make a crew's cardiovascular system suffer for a sustained year are also the mechanism that makes their return younger than the world they left. The engine strain, the G-force limits, the punishing energy costs catalogued earlier tonight. All of it is inseparable from the reason a traveller comes home to grandchildren instead of the same faces that waved goodbye. The cost and the reward were never two separate line items on this journey. They were the same maneuver, felt from two different sides of a single accelerating body. Nobody needs to travel anywhere near light speed to prove this. GPS satellites, orbiting Earth at speeds and altitudes considerably gentler than anything discussed tonight, experience both effects simultaneously: a small velocity-based slowing from their orbital speed, and a small gravitational speeding up from sitting higher in Earth's gravity well than a clock on the ground. Engineers correct for both discrepancies in the satellite's software every single day, because a navigation system blind to relativity would drift by several miles within 24 hours. The twins in this story are not a thought experiment confined to spaceships nobody has built. They are already, quietly, keeping every phone's map accurate. A body does not need to leave Earth at all to be one half of this experiment. It only needs a clock precise enough to notice, and 40 years to wait for the reunion. The same patient arithmetic, running unnoticed overhead every day, that this entire episode has simply carried out to its far more dramatic, far more distant conclusion. Strip away every proposed engine, every paper mission, every mathematically clean profile described so far tonight, and here is what human beings have actually built and tested. A spacecraft concept called a light sail, a few meters across, thinner than a soap bubble, attached to a probe smaller than a smartphone, designed to be pushed not by fuel, but by the sustained pressure of a ground-based laser array powerful enough, briefly, to rival a fraction of a large city's entire electrical output. On paper, a fleet of these postage stamp-sized probes could reach roughly 20% of light speed, reaching the nearest star system in about 20 years of flight, instead of the tens of thousands a chemical rocket would need. The project proposing this, backed by serious funding and serious physicists, has spent years working through the individual pieces: the laser array, the sail material, the tiny onboard camera and radio strong enough to send a single image home across 4 light years. Every piece of that plan is being treated as an engineering problem with a real timeline, not a thought experiment for a lecture hall. 20% of light speed sounds modest, next to the 90 and above percentages catalogued earlier tonight, and that gap is precisely the point. Even at a fifth of c, the probe still crosses interstellar space in a fraction of the time any chemical rocket could manage, still experiences a measurable, calculable degree of time dilation, still has to survive a real, modeled rate of dust impact. It is relativistic travel's genuine, achievable flaw, the smallest meaningful step past ordinary spaceflight. Attempted first specifically because it is the cheapest place on this entire curve to fail. Now scale that same physics down rather than up. Even at this size, the same hazards catalogued tonight do not disappear entirely. Dust and stray atoms would still batter a gram-scale sail at 20% of light speed, and mission designers have already had to model exactly how many of these fragile probes would likely be destroyed in transit, accepting in advance that only a fraction of any launched fleet would survive to report back. The story does not need a human body aboard to still be, fundamentally, a story about fragile things trying to survive a fast crossing of mostly empty space. Because nothing about that tiny probe needs to survive what a body would. There is no radiation dose limit to track, no bone marrow at risk. A cardiovascular system has nothing to strain against, since the laser does the pushing from safely back on Earth in a matter of minutes, not years. The mission ends there too. No return trip, nothing to decelerate, nobody waiting on a reunion. It is, in the most literal sense, the easiest version of this entire journey, precisely because there is no traveler aboard it to keep alive. This is the honest measure of the gap between what tonight's story describes and what current engineering can deliver. Humanity's most advanced real proposal for relativistic travel carries no body at all, and even that unmanned version remains, as of tonight, a design on paper and a handful of successful ground tests, not a launched mission. Every dust impact, every radiation dose, every mass energy wall catalogued in this episode is not a hypothetical curiosity dreamed up for the sake of a good story. It is the actual, unsolved engineering gap standing between the smallest thing we have ever proposed sending this fast, and the first human body that might one day follow it. Every hazard catalogue tonight has an engineering answer, however expensive, however incomplete. Shielding, torpor, redundancy, a slower and gentler profile. There is one part of this journey that no material, no protocol, and no amount of funding has ever been able to soften, because it isn't a hazard to the body at all. It is a hazard to the mind carrying it. Psychologists who study isolation, polar researchers, submarine crews, astronauts on long-duration missions already describe a phenomenon they call anticipatory grief. Mourning a loss that has not yet happened, but that has become mathematically certain. A relativistic traveler does not merely risk losing the people they left behind to time. They know, with the same certainty as any equation in this episode, that the loss is already underway the moment the engines ignite, ticking forward on a schedule no acceleration burn will ever pause. Existing astronaut psychological support, built for missions measured in months, has no protocol for a separation measured in decades, experienced as months by only one side of it. There is no support group on Earth composed of people who have lived through what this crew is about to live through, because until now, nobody ever has. Whatever a real crew brings with them on a journey like this, training, resilience, whatever version of hope makes the math bearable, they would be building the very first playbook for a specific, quantifiable kind of loss in real time with no one to call who has already been there. And that may be the most honest answer this entire night can offer to the question of what happens to a body approaching light speed, long before the wall at sea, long before the last survivable dose of radiation. The thing a traveler would actually have to learn to carry is the plain, arithmetic knowledge that somewhere behind them, in a direction their own ship's light can no longer meaningfully reach, an entire life is quietly finishing without them. No centrifuge, no radiation vault, no simulator has ever been built that can rehearse a person for that specific feeling in advance. The closest anyone has come is talking, slowly and honestly, with people who have survived long, one-way separations of their own, deployed soldiers, long-haul researchers, immigrants who left knowing a return might never come. They do not fully translate, because none of them ever had to watch it happen on a clock that would not lie to them about exactly how much they had already lost. Mission psychologists who have started thinking seriously about this problem keep arriving at the same uncomfortable recommendation. Select crews not for their ability to suppress the grief, but for their capacity to metabolize it slowly, in public, without it curdling into something a small, isolated group cannot survive living alongside for years. Nobody has tested whether that capacity actually exists in a person until the ship is already too far from home to turn back and find out. In August of that year, between the Apollo 16 and Apollo 17 missions, the Sun released one of the most powerful solar particle events ever recorded by human instruments. A burst of radiation intense enough that, had astronauts been walking on the lunar surface, or in transit through open space when it arrived, the dose could plausibly have been lethal within hours, not years. No crew was in transit that week. The timing was coincidence, not planning. This was not deep interstellar radiation. It was our own ordinary sun, doing something it does occasionally and mostly harmlessly to a planet with a thick atmosphere and a strong magnetic field wrapped around it for protection. Strip away that shielding, put a body in a thin-walled spacecraft, or on an unprotected lunar surface, at the wrong 72 hours in an 11-year solar cycle. And one of the most ordinary stars in the galaxy nearly killed a human being who had done everything else about the mission correctly. Radiation biologists who later reconstructed the event estimated the dose an exposed astronaut would have absorbed, and the number falls in the range associated with acute radiation sickness. Nausea and vomiting within hours, a collapsing blood cell count within days, and the substantial risk of death within weeks without immediate and sophisticated medical care. No lunar mission of that era carried aboard. NASA now treats this single week as one of the defining case studies in every subsequent mission's radiation planning, including current design work for crewed Mars missions that would spend months, not days, exposed to the same unpredictable Sunday. What makes the near miss so useful decades later is precisely how ordinary its cause was. This was not a supernova or a gamma ray burst. Not any of the exotic sources of radiation this episode has otherwise catalogued. It was our own familiar sun, doing something well within its normal, recorded behavior, at a moment that simply happened to fall between two missions instead of during one. Mission planners now speak of solar weather with the same seriousness meteorologists reserve for hurricanes. Trackable, seasonal, and still, on occasion, lethal to anyone caught outside without shelter. Hold that number. A near miss, decades ago, using nothing more exotic than the sun humanity was born under. At a distance humanity has already safely crossed with living bodies 6 separate times. The interstellar radiation catalogued throughout this episode is not a hypothetical escalation of that danger. It is a permanent, unrelenting version of the same category of event that, for 1 week in 1972, very nearly proved fatal purely by accident of scheduling, which is the detail worth sitting with before this story turns toward its final numbers. Humanity has already had one honest preview of what unshielded radiation can do to an unlucky body in space, delivered by the gentlest star available to us, and absorbed only because nobody happened to be standing in the wrong place when it arrived. Every dose calculation cited earlier tonight. For a crew crossing interstellar distances at relativistic speed, describes a version of that same August week that never ends. Not a single unlucky flare to survive, but a permanent, continuous storm with no 11-year cycle offering a season of relative calm, and no lunar module to climb back into once the numbers stop looking survivable. Engineers did not wait for better computers or newer physics to start designing a ship for exactly this journey. In the 1970s, a volunteer group of scientists and engineers spent years producing a fully worked design for an unmanned probe intended to reach another star system within a human lifetime using nuclear pulse propulsion. Thousands of small fusion detonations, one after another, each pushing the ship a little faster against a blast plate at its rear. Their design, on paper, could reach roughly 12% of the speed of light, arriving at a nearby star within about 50 years of launch. The study ran for years, filled multiple published volumes, and remains, decades later, one of the most detailed interstellar propulsion designs ever completed by serious engineers rather than science fiction writers. It solved, in real technical detail, the fuel chemistry, the pulse unit sequencing, the structural loads on a blast plate absorbing thousands of consecutive detonations. It did not solve, because it was never asked to, what any of that would do to a person strapped in behind it. The volunteers behind that design chose an unmanned probe specifically because they understood, even in the 1970s, that adding a crew would multiply the difficulty of the project by an order of magnitude. No single study group could realistically absorb shielding mass, life support, deceleration for a safe landing rather than a one-way flyby. Every one of those additions was set aside, deliberately, so the propulsion physics could be proven on its own terms first. Now apply everything catalogued tonight to a design conceived half a century ago, decades before anyone had modelled interstellar radiation dose with real seriousness. That original blueprint carried no meaningful shielding, no accounting for dust impact rates now considered basic due diligence, no consideration at all for a crew, because it was never meant to carry one. It was audacious specifically because it didn't have to solve a single one of the problems a living body introduces. Add a human passenger to that same design, and every number in this episode, the radiation, the mass wall, the deceleration budget, reattaches itself immediately. turning a 50-year unmanned probe into a proposition no engineer of that era, or arguably this one, has ever fully solved for a person expected to survive the trip. The blueprint proves the propulsion problem was never the part holding this back. It proves, instead, exactly where the actual bottleneck of this entire story has been sitting all along. Not in engines, not in fuel, but in the stubborn, irreducible fragility of the body any of this was ever for. Every decade since has produced a newer version of the same study, swapping fusion pulses for antimatter, for laser sails, for concepts not yet named, and every version arrives at the identical structural truth. Propulsion keeps getting cheaper to design on paper. The body keeps costing exactly what it always has, because marrow, corneas, and inner ears do not benefit from 50 years of better computer modeling the way blast plates and fuel tanks do. Every engineer who has ever revisited that original 1970s design has had to add the same missing chapter back in, and none of them have ever finished it to anyone's full satisfaction. A human body is not the only thing aboard this ship, silently accumulating damage it cannot repair. The hull, the structural beams, the very metal holding the vessel together, absorbs the same relentless bombardment of dust and radiation described earlier. And metal, unlike bone, has no mechanism at all for healing itself. Materials scientists have a name for what sustained particle bombardment does to a metal's internal structure over years: embrittlement. Every high-energy particle that slams into a girder or a hull plate can knock individual atoms out of their orderly lattice, leaving behind microscopic defects that accumulate, one collision at a time, until a metal that was flexible and forgiving at launch becomes measurably more brittle, more prone to sudden fracture under stress it would once have absorbed without complaint. Nuclear reactor engineers already track this exact process in reactor vessel walls here on Earth, replacing components on a schedule dictated by embrittlement long before the metal shows any visible sign of wear. A relativistic hull ages by this same mechanism, continuously, for the length of the crossing. A slow hardening and weakening that has nothing to do with rust, nothing to do with fatigue from ordinary stress, and everything to do with the same bombardment threatening the crew sealed inside it. Engineers designing for a mission like this have to schedule structural inspections the way a hospital schedules blood work, watching for a kind of aging that no amount of external polish or paint would ever reveal from the outside. Now combine that reality with everything else already accumulating aboard the same ship. Different metals embrittle at different rates, which is why real reactor engineering favors specific alloys, chosen partly for how gracefully they degrade under bombardment, rather than how strong they are on the day they're installed. A relativistic hull would need the same careful selection, prioritizing a slow, predictable decline over raw strength that fails without warning once its hidden threshold is finally crossed. So the ship, in its own slow, metallic way, is undergoing something that rhymes with what its passengers are experiencing. Both are accumulating a kind of damage neither chose and neither can fully repair, on a timeline dictated entirely by how long the crossing takes and how fast it dares to go. The hull will not feel it the way a body feels a bruise. It will simply, one day, be less able to forgive a stress it would have shrugged off on the day it launched. The same quiet arithmetic of accumulated cost that has been running underneath every other system in this story since the very first grain of dust struck. There is a strange, unspoken kinship in this. The crew and the hull around them are, in the most literal engineering sense, aging together, exposed to the identical bombardment, measured by the identical clock, neither one able to simply opt out of the wear the crossing demands of it. Two different kinds of matter, discovering the same cost from two different angles, strip away every hazard already catalogued, and one more cost remains, small enough to sound trivial and large enough to matter for a body sealed inside a hull for years. The view out the window simply does not change. A single, tightening point of light ahead. A well of black behind. No passing scenery, no changing horizon, no new terrain to notice on a walk, for as long as the cruise phase of the mission lasts, which, for a journey of any real interstellar distance, is most of the years the crew will spend awake and aware aboard the ship. Sensory and environmental psychologists who study prolonged isolation in Antarctic research stations and submarine deployments already describe a specific, measurable toll from environments that offer no meaningful visual novelty. Attention narrows, mood flattens, and the ordinary human hunger for a changing world goes unfed for months at a stretch. A relativistic crossing does not offer months of this. It offers years. Inside a view that cannot be walked away from, redecorated, or waited out, because the geometry producing it will not relax until deceleration finally begins. Mission designers already treat this as seriously as any radiation dose. Proposing interior murals, virtual windows displaying recorded Earth scenery, deliberately varied lighting cycles, anything that gives a starved visual system something to metabolize besides the same single point of light. Night. After identical night, Antarctic winter-over researchers, living through months of unchanging darkness, already report exactly this kind of flattened perception. Days blurring together, ordinary landmarks of time losing their grip, until a calendar becomes the only reliable evidence that time is still passing at its usual rate at all. A relativistic crew would face a version of that same blurring stretched across years instead of months, with no changing season, to eventually break the pattern and no flight home scheduled for the following spring to look forward to counting down toward. This is among the smallest hazards in this entire episode, and among the easiest to underestimate for exactly that reason. A body can survive radiation, survive isolation, survive years of sameness, and still arrive having paid a real, measurable cost for the simple, cumulative fact that nothing outside the window was ever willing to change. It is also, oddly, one of the few hazards in this story with a genuinely simple fix, at least in part. A screen, a recorded loop of clouds and coastline, a lighting rig that mimics a sunrise nobody outside the hull will ever actually see again for years. None of it restores the real thing, but each of it gives a starved visual system somewhere else to rest besides a single, unblinking point of light, at a cost measured in kilograms rather than in anything approaching the price of shielding or fuel. Even a borrowed, artificial version of an ordinary sky turns out to be worth the mass it costs to carry all the way there, all the way to wherever this particular crossing finally ends. Picture the mission this entire night has been steadily assembling, piece by piece. A crew departs, accelerating at a steady 1G through the dust and thinning radiation of the years catalogued earlier. They pass 50% of light speed within months, 90% within a couple of years, climbing toward the midpoint of their outbound journey where the curve described earlier finally starts to bite. Real mission designs, the ones engineers can actually defend in front of a funding committee, do not chase that curve all the way to its most extreme, most expensive decimals. They stop accelerating somewhere in the 80 to 95% range. Not because the crew ran out of nerve, but because every additional 9 past that point costs more than the entire mission budget spent reaching it. The ship settles, briefly, into its fastest sustained velocity of the entire crossing, still gaining a survivable, humanly meaningful 2 or 3 years for every decade left behind on Earth, without gambling the whole mission on an engine trying to buy one more decimal point nobody could actually afford. This is the real shape of the wall discussed throughout this episode, translated out of pure mathematics and into an actual flight plan. Not a barrier a real ship slams into and shatters against, but a curve real engineers simply choose to stop chasing at the exact point where the next unit of speed stops being worth what it cost the mission to buy. The traveler does not reach the edge of what physics allows, they reach the edge of what the budget allows, which sits, by design, at a comfortable, calculated distance from the true wall. close enough to make every fact in this story real, far enough to leave a margin no engineer would ever spend down to zero. There is no dramatic klaxon at this moment. No crew gathered anxiously around a console watching a needle strain against a red line. The engines simply throttle back to a lower, sustainable thrust, holding the ship at its cruising fraction of light speed for the long, silent middle of the crossing. The exact stretch where radio silence closes in, where the sky ahead has already tightened into its single point of light, where a body's own clock has already begun falling behind everyone who stayed home. The most extreme physics in this entire story is not a moment the crew experiences as a crisis. It is a setting on a dial, chosen months earlier, that they simply live inside for years without any alarm ever telling them it happened. And it is here, cruising at the fastest speed the mission will ever reach, with nothing left to accelerate toward and nothing left to decide, that the actual shape of everything this night has catalogued finally comes into full view. Not as a list of separate dangers, but as a single, connected cost. Reconsider. From this cruising altitude, everything catalogued so far, and a pattern emerges that no single segment was built to reveal on its own. Strip away the hull, and the dust and radiation were always about a body remaining recognizably itself. Its marrow, its cornea, its unmutated cells. Inside a universe that treats a fast enough traveler as fair game for every particle it has ever flung across the dark. The engine was never the real subject of the mass wall either. Underneath it sat a body's own inertia, turning into a debt owed to physics, payable only in energy no civilization has ever produced. And the dilating clock had nothing to do with the ship at all. What it actually measured was a body continuing, faithfully, to be exactly itself, while the people who defined its sense of home quietly stopped waiting and started simply living without it. Every hazard in this episode, looked at from here, is a version of the same single demand, that a body approaching light speed keep negotiating what it is willing to become. Heavier, to anyone measuring from outside, unchanged to itself, later to every calendar it left behind. Alone, in a present tense that no other living person will ever again fully share. None of this was ever a single threshold to cross, the way the opening of this story implied. A speed where skin stops being safe, a wall no body has crossed. It was always this, a slow, continuous renegotiation of what a body is, conducted the entire length of the journey, with no clean finish line marking the moment the negotiation ends. This is not a comforting reframe. It is a more accurate one. The traveler this story has been describing does not survive light speed the way a stunt is survived. Endured once, then finished. They live inside an ongoing exchange between the body they still recognize in the mirror and the body an outside universe insists on measuring differently for as long as the engines keep the ship above the ordinary speeds where that exchange falls silent. Every fact catalogued tonight, from the first grain of dust to the last unreachable decimal of C, was simply one more term in that same single negotiation. Even the hull embrittling by degrees, even the window that refuses to change, belong to this same negotiation. Seen from a slightly different angle, a ship is not a neutral container carrying a fragile passenger through a hostile universe. It is itself another body, aging by its own rules, negotiating its own version of what it is willing to become before the crossing is done. Nothing about the destination changes this. Whatever the crew eventually reaches, wherever the ship finally powers down and lets its passengers step out into gravity that isn't manufactured by their own acceleration, the negotiation this journey required has already happened, continuously, the entire way there. The wall at light speed was never the point where the story ends. It was simply the outer edge of how far that negotiation could ever be pushed. And every traveler in this story reaches their own personal edge of it, long before the mathematics ever does. Deceleration. When it finally comes, mirrors the acceleration that started this journey so many years and so few years. Ego, the same steady 1G, reversed, easing the ship back down from its cruising fraction of light speed towards something a body can step out into without being killed by the difference. The tightened point of light ahead begins, slowly, to relax back into a scattered field of individual stars. The deep well of darkness behind begins filling back in with the ordinary, familiar dust of a galaxy no longer being compressed by velocity into something unrecognizable. The traveler stepping off that ship will have aged some careful, survivable number of years, the exact figure depending on how close to the wall the mission was willing to fly, how long the cruise lasted, how gently the engineers chose to spend their fuel. Whatever that number is, it will be smaller, often dramatically smaller, than the number waiting for them on every calendar, every gravestone, every institution back on the world they left. Not because anything went wrong, because everything, from the first grain of dust to the last percent of light speed this mission dared to spend, went exactly as the equations said it would. This is the arrival every calculation in this story has been steadily building toward. Not a triumphant landing, though it may look like one from the outside, but the moment two different amounts of elapsed time, carried by two different bodies, are finally set down next to each other and compared. One of those amounts belongs to a traveller who did everything asked of them, absorbed every hazard this night has catalogued, and arrives feeling, from the inside, exactly as unremarkable as they did the day they left. The other belongs to everyone who never left at all and simply kept living, the entire time, at the ordinary, unhurried pace the rest of the universe has always used. There is no instrument aboard that ship capable of measuring the second kind of time directly. It can only be inferred, calculated in advance, and then confirmed the moment a hatch opens onto a world that has finished 40, 60, 100 years of its own history without waiting for confirmation that the mission had gone well. Every fact catalogued across this entire night. The dust, the radiation, the tightening sky, the mass that refuses to stop climbing, was always in service of producing this exact number, this exact gap. Whether the crew ever consciously thought of the mission in those terms or not, nobody aboard that ship chose this trade lightly. Every one of them understood, before the engines ever ignited, that the price of seeing what waited at the other end of this velocity was measured not in fuel or risk alone, but in a specific, quantifiable portion of every relationship they were leaving behind. They went anyway. That too is a fact this story has been carrying the entire time, largely unspoken. So here, finally, is the full answer this night set out to find. It is not frozen or crushed or torn apart by the speeds this story has climbed through. It is bombarded by dust turned into bullets, aged by a clock that never once feels like it is slowing, quietly negotiated for by marrow and cornea and inner ear, and priced at every single decimal of the approach. By a mass that costs more to move the closer it gets to a wall, it is mathematically forbidden to ever touch. None of that arrives as a single dramatic instant. It arrives the way this entire episode has unfolded. Gradually, continuously, one honest fact layered on the last, for as long as the engines keep burning, which means the true answer was never about a threshold, a wall, or a single terrifying moment of transformation. Your body never slows down at all, not for one instant, not by any amount it could ever feel from the inside. What changes, permanently and without your permission, is everyone else's. The clocks you left. The faces that will have aged past, recognizing you as easily as you recognize them. The whole quiet, ordinary universe that keeps its own pace precisely because you, for a while, stopped keeping pace with it. And that is not a verdict on the journey. It is simply what the journey is made of. The same trade, in miniature, that this quiet universe has always been offering anyone willing to move through it. Distance measured in what you're willing to let keep aging without you, so that you can see, just once, how far the dark actually goes. It remains an open question, largely untested, still capable of surprising the first body that ever actually tries it. Nobody has gone yet. The wall is still there, waiting, exactly as far away as it always was. We've drifted through dust turned lethal by nothing but speed, through a sky that folds itself into a single point of light, through a clock that never once admits it is falling behind. Together, we've followed a body all the way to the edge of what physics allows it to become, and back again into a present tense that was still, somehow, waiting for it. You are not that traveller, not tonight. Tonight, you are exactly as fast as the Earth's turning, exactly as far from home as your own bed, and every clock in your life is still keeping the same time as everyone who loves you. If your eyes feel heavy, let them close. That too is the body doing exactly what it was always going to do. If this felt like the kind of night you return to, leave a comment when you wake up. And if you're still here, awake, the next chapter of this quiet universe is already waiting. The universe will still be here when you wake up. So will we. Good night.